Welcome to my Static Timing Analysis STA series. This is a 4-part series, and by the end of it, my goal is that you will feel comfortable with the fundamentals of static timing analysis and understand the timing equations used in digital design. Here's what we will cover. Part 1, Contamination Delay and Propagation Delay. Part 2, Setup Time, Hold Time, and Clock to Queue. Part 3, Clock to Queue Contamination Delay and Clock to Queue Propagation Delay. Part 4, Clock to Skew. So let's jump into Part 1. So what exactly is static timing analysis, or STA? STA is a method used to verify that the digital design can operate correctly at a given clock frequency. A synchronous digital design is made of two basic building blocks: registers, or flip-flops, combinational logic between them. Data is launched from one register, traveled through combinational logic, and is captured by another register. The important thing is that it takes time. So some paths are short, some paths are much longer. For example, suppose one path takes 1 nanosecond, while another takes 2 nanoseconds. If we ignore the flip-flop delays for now, the clock period must be long enough for the longest path. That means that if the longest path is 2 nanoseconds, the clock period cannot be smaller than 2 nanoseconds, which corresponds to a frequency of 500 MHz. In reality, we will later see that we also need to account for the flip-flop timing. But for now, we're only focusing on the combinational logic. The first timing parameters we will learn are propagation delay, the maximum time it takes for a signal to propagate through a combinational logic. Think of it as the slowest possible path. Contamination delay, the minimum time before the output of the combinational logic begins to change. Think of it as the fastest possible path. Combinational logic includes things like logic gates, multiplexers, encoders, decoders, and so on. Let's see how we calculate these delays in a real design. Before we start calculating delays, let's define what a timing path is. A timing path is the route that the data travels from the output Q of a launch register or from an input to the input D of a capture register or to an output. A single destination can have multiple timing paths, and in static timing analysis, we analyze each path independently. Now let's calculate the delays of the different timing paths in this circuit. Let's start with the path from X to D1. The signal first passes through the AND gate, which has a delay of 2 nanoseconds. Then it passes through the OR gate, which adds another 3 nanoseconds. So the total delay of this timing path is 2 plus 3 equals 5 nanoseconds. Now let's look at the first path from Q0 to D1. This path also goes through the 2 nanosecond AND gate, followed by the 3 nanosecond OR gate. Again, the total delay is 5 nanoseconds. But there is actually another timing path from Q0 to D1. This one bypasses the AND gate and goes directly through the OR gate. That means its total delay is only 3 nanoseconds. So notice that the same start point and end point can have multiple timing paths. Now let's determine the propagation and contamination delays. For the path from X to D1, there's only one timing path. Since there is only one possible route, both the propagation delay and the contamination delays are 5 nanoseconds. For the path from Q0 to D1, we have two possible routes. The slowest path takes 5 nanoseconds, so the propagation delay is 5 nanoseconds, and the fastest path takes 3 nanoseconds, so the contamination delay is 3 nanoseconds. Remember, propagation delay is always the slowest, and contamination delay is always the fastest. For this video, we are going to make one important simplification. We will assume that the only timing delays in the system come from the combinational logic. In reality, flip-flops also introduce timing delays. Since our longest propagation delay is 5 nanoseconds, we will choose a clock period of at least 5 nanoseconds. That corresponds to a maximum clock frequency of 200 MHz. Any frequency at or below 200 MHz will satisfy this simplified timing model. In the next video, we will make it more realistic by introducing the timing characteristics of flip-flops: setup time, hold time, clock-to-Q delay. Once we include those, we will be able to calculate the actual timing constraint used in real FPGA and ASIC designs. Thank you for watching, and I will see you in part 2.